Okay, welcome class. So, in the previous class we are discussing about the analytical solution of the matrix differential Riccati equation. So, we have seen one approach in which we use the state transition matrix to determine the solution of matrix differential Riccati equation. Our approach was for a given system x dot equal to x plus bu, y equal to cx, we are finding out the ut by minimizing the performance index as half of x prime tf, f of tf, x of tf plus half of integral t0 to tf x prime t q t x t plus u prime t r t u t. So, we have to minimize this performance index subjected to the plant. Objective is to find out the minimum value of the u. So, in finding the u, basically our u is, so ut we determine as minus r inverse function of t b prime pt xt. So, in finding the u, we have to find out the pt, which is the solution of my matrix differential Riccati equation given as p dot t minus A transpose P plus PA minus P B R inverse B prime PT plus QT. So, objective is to find PT, and so in this formation we start our solution with the Hamiltonian system given as x dot t at minus et minus qt minus a prime t xt lambda t. So, if you will see, this is nothing but a set of first order differential equations, similarly as given as the x dot equal to ax. So, what we do, we find out the state transition matrix of Hamiltonian matrix, and then we make the partition of this as we have seen in the previous class, and then we find the PT is nothing but equal to phi 21, phi 22, phi 11, phi 22 and f of tf. What is phi 1 matrices? So, phi T T0 is my state transition matrix, and this we partitioned as phi 11, phi 12, phi 21 and phi 22. So, if we partition this matrix in this form, then with the help of this we can find out PT, which we have seen in the previous class. So, first we will see the application of this, taking a very simple example and see how it can be utilized to find out the matrix PT. So, we take the same example which we have discussed before. We have a plant given as x dot t to xt plus ut. We are taking a first order system which will give me the second order Hamiltonian, which can be easily solved by the manual approach. If our system will be the bigger, then we have to take the to use the computer to solve this matrix. So, my system is given by this matrix and Pi is one by 4 u square t dt. So, our objective is to find out the u, which is minus r inverse b prime p, and p is the solution of my matrix differential Riccati equation. So, if I know the p, I can find out the u. So, we will take this state transition matrix approach. So, first we have to define what will be my Hamiltonian matrix. To define the Hamiltonian matrix, I must know what is my matrix A. In this case is x dot is 2x, nothing but 2, b equal to 1 ut. Then I need the E. E is nothing but b r inverse b prime. So, this is b is 1, r inverse is, so r is my, say if you will see here q is 3 and r is 1 by 4. So, 1 into 4 into 1, which is, so E is nothing but my 4. So, if I will write my Hamiltonian matrix x dot t lambda dot t, this is equal to nothing but my A is 2 minus E, so minus 4, then minus Q minus 3 and A transpose, this is 2, so minus A transpose is minus 2. So, this is nothing but my Hamiltonian system or Hamiltonian matrix. So, we call it node matrix. This is my Hamiltonian system. And this multiplied with x t lambda t. So, for this Hamiltonian matrix delta, we have to find out the state transition matrix. So, state transition matrix of delta we will represent as phi t T0, which is nothing but my e to the power delta t, and we can write as the inverse Laplace of SI minus delta inverse. So, delta is given here. So, if I will take SI minus delta inverse of that, this will give me nothing but my state transition matrix. What we can write for this is nothing but my inverse Laplace of SI minus A inverse. And what is my SI minus A? So, this will be nothing but my S 0 0 S, sorry, it is not A, we are using SI minus delta. So, this will also be my SI minus delta which we are using there. So, SI minus delta, delta is 2 minus 4 minus 3 minus 2. So, if I will write this is simply my S minus 2 4 3 and S plus 2. So, I have to take the inverse of this matrix, which by the standard procedure we can do this. We take the inverse of this and then take the inverse Laplace of this. So, if we will follow this, we can write phi t0 as, I am directly writing the result. So, 1 by 4 3 e to the power 4 t minus t naught. My second element is 1 by 2 minus e to the power 4 t minus t naught plus e to the power minus 4 t minus t naught. This is my first row, and second row is 3 by 8 minus e to the power t naught plus e to the power minus 4 t minus t naught. Second element is 1 by 4 4t minus t naught plus 3 e to the power minus 4 t minus t naught. So, this is my state transition matrix when we are evaluating it from t0 to t. So, if you will recall, this state transition matrix we have to determine. So, phi T2 TF, if I will say. say as j we have taken T1. So, we will take this as T0 to T1. So, we can write this matrix simply as just these terms I have to reverse. So, it is the same matrix like 1 by 4 3 e to the power 4 t minus T1 I have missed one thing. This is plus e to the power minus 4 t minus t naught. So, this I have missed. So, I have added this term here 3 to the power 4 t minus t1 plus e to the power minus 4 t minus t1. This is my first term. Second term is 1 by 2 minus e to the power 4 t minus t1 plus e to the power minus 4 t minus t1 is my second term. 3 by 8 minus e to the power 4 t minus t1 plus e to the power minus 4 t minus t1 we are doing t minus t1 and 1 by 4 e to the power 4 t minus t1 plus 3 e to the power minus 4 t minus t1. So, this is the same matrix here, but here it is T0 to T, then here we have T1 to T. So, this state transition matrix we have partitioned as the 4 element. The first one will be my phi T1 phi 1 T1, this is phi 1 phi 2 and this will be my phi 2. And if I will see what is my matrix P, this is phi 21, phi 22 into F, phi 11, phi 22 into F. What is F of TF in this case? FTF is 0 because we have not considered any terminal cost in defining the J. So, these are the values of phi 11, phi 12, phi 21, phi 22. So, I can directly write what will be the solution of the matrix Riccati equation. So, as my f of TF is 0, so my this term and this term will be 0. So, my PT is phi 21 multiplied with the phi 11 inverse. So, PT I can directly write as phi 21 phi 11 inverse. And what is my phi 21? 3 by 8 minus e to the power minus 4. So, this I can simply write as, so I am writing nothing but phi 1, this is 3 by 8 this term. So, this is my phi 2 1. E to the power 4 t minus t 1 plus e to the power minus 4 t minus t 1 multiplied with phi 1 1, which is 1 by 4, this is 3 e to the power 4 t minus t 1 plus e to the power minus 4 t minus t 1 and inverse of this. So, TF is 0, sorry, f of TF is 0. So, this term and this term will not appear. So, I am only with the phi 2 1, phi 1 1 inverse. So, I can write this, and if I will simplify this, I will simply get, writing the final result as 3 by 2 1 minus e to the power 8 t minus t 1 divided by 1 plus 3 to the power 8 t minus t 1. So, this will be my nothing but Pt. If Pt is known, I can directly write what is my Ut. This is minus R inverse B prime Pt xt. R inverse is 4, B prime is 1. So, this is nothing but minus 4 Pt into xt, where Pt is given by this equation. So, this will be my Ut. So, directly I can implement my closed loop control. So, by this example we have seen the application of the determination of analytical solution of matrix differential Riccati equation utilizing the state transition matrix approach. Next we will discuss the another approach which is based on the eigenvalue and the eigenvector analysis. So, my another approach for the analytical solution of the matrix DRE is based on eigenvalue and eigenvectors. Again we use the Hamiltonian matrix to obtain the solution. In this approach we can find out the transient and the steady state solution of matrix differential Riccati equation, and this method involves the calculation of the eigenvalues and eigenvector of the Hamiltonian matrix or Hamiltonian system we say. As we know what is my Hamiltonian system, we already have discussed this. X dot lambda dot t is A minus E minus Q minus A prime x lambda, where E is nothing but B R inverse B prime. So, again first we are discussing, say here A, E, Q, A all are the function of time. So, we are taking the time varying system, but for the simplicity this T has been dropped from the matrix A, E, Q, A prime. Closed loop LQR gain we can determine simply as using the transformation lambda t equal to PT xt, which we have seen in the derivation of our Riccati equation. So, our transformation matrix is lambda t PT xt, and my matrix differential equation I am writing as PT A minus A prime P Q P B R inverse B prime P with boundary condition is PTF equal to F of TF. So, to determine the solution of matrix differential Riccati equation means we are trying to obtain the value of PT, which can be expressed in terms of the eigenvalues and the eigenvector of my matrix, Hamiltonian matrix. So, we are defining our Hamiltonian matrix as A, either I can write E or I write B R inverse B prime minus Q A transpose. So, all these expression I have dropped out the T term, that is only for the convenience or easy representation of this, otherwise my matrix A, B, R, Q, they all are time varying, they all will depend the T. So, in this we give a statement if mu is the eigenvalue of delta, then minus mu is also an eigenvalue of delta. So, this we can prove considering a transformation matrix which we are saying as the tau given as the 0 I minus I 0, where I is the identity matrix of order n cross n and 0 is the null matrix of order again n cross n. So, because my Hamiltonian matrix is 2n cross 2n matrix, where n is the order of my system. So, we also consider this transformation matrix as 2n cross 2n. The property of the tau is, if I will take the inverse of this, which I can simply verify, this is nothing but the minus times of tau. This means this is nothing but 0 minus I 0. Now, this transformation matrix is utilized to prove this condition, which we are saying if mu is the eigenvalue of delta, then minus mu is also an eigenvalue of delta, where delta is my Hamiltonian matrix. So, we will see this proof in the next class. This class I will stop here. Thank you very much.